Okay. All right, so today we're going to go through the 8.3 notes on Euler's method, and yes, that word is pronounced like oil, not Euler. Not Ferris Bueller, this is Euler. And maybe we'll get a chance in class to talk more about Euler himself, who's a pretty interesting character. But we'll also talk about slope fields in this lesson. I'm going to leave a lot of the slope fields examples undone in this video, but they will be filled in on Google Classroom, so make sure that you check your work on those. But first, I want to point out, I've already done this warm-up, but I recommend that you try it by yourself, just to make sure that you are really comfortable with the 8.2 notes. This is an important example, as I've noted here, because as we kind of previewed a little bit last class, anytime that I integrate and I end up with natural log of y as my solution, as part of my kind of initial solution, that's a time in which I do not want to solve for c right away. I actually recommend solving for c right away in all of the other cases except for this one. In the end, it doesn't really matter, but this one in particular makes it easier if you isolate y first by exponentiating, and then using exponent properties to say that this e to the c is just another constant, kind of that idea that we can write a constant as any c we would like. So I put it as a c in front. That makes it really easy because especially when you're given an initial condition, y of 0, that c is your initial condition because e to the 0 is 1. So anything that we would be multiplying by, or anything that we would be setting it equal to would be just equal to c. And that makes it a really easy solution. So highly recommend trying this yourself. Look back here if you need some help. Okay, but just a quick recap before we get into the method for today. Is our goal in this unit is to solve differential equations. And differential equations are anything that has a derivative, dy dx. In BC Calculus, we're only going to deal with first order differential equations, which means things that only have the first derivative. Maybe we will deal with a second order differential equation in the sense that we'll be given the acceleration and I would like you to find the position kind of things. But for differential equations category, we're usually just given the first derivative in some equation. And there are three methods we're going to use in BC to kind of solve these differential equations. And the first we've already done, separate and integrate. This is where we get a y equals equation. If we have a plus c, we call it a general solution. If we have an initial condition to plug in, we call it a particular solution. And in a particular solution, there should be no plus c's. What we're going to do today is talk about how to solve graphically using slope fields, and also numerically. So if we wanted to approximate some value, if we were given an initial condition and maybe we couldn't solve for whatever reason, we couldn't separate and integrate, we could use Euler's method to find an approximation for another value on that function. So we're going to start with Euler's method and then we'll move to slope fields. Okay. All right, so to kind of give us a reason as to why we would need Euler's method, or how to use Euler's method, the first thing I want you to do is graph the solution that we found in the warm-up. That solution was y equals e to the x. I have that graphed here and marked my initial condition 0, 1. Okay, but let's say that we couldn't have solved this in some scenario, okay? Or we would like to get kind of a decimal approximation for an answer. How could we approximate the value of y of 2 if we were unable to find the solution? Okay, so I know that you all can now plug in and say that y of 2, given the solution above, would be e squared. But how could we find kind of a decimal approximation for that? What would be this approximately? So this is where Euler's method comes in, but it's based off of a very simple concept back from chapter 3. And we have to use a tangent line to approximate this. So because we are given a slope and we are given a point, we are able to write a tangent line to this graph at this point. So using my slope, let me write this in a different color. Okay, so slope, which is dy dx, and my point, y of 0, okay, I am going to write an equation, the equation of the tangent line. Okay, so first I want to make sure I know the slope at the point I'm looking for. Okay, luckily that slope is just 1. Okay, and if we put it all together, I would get y minus 1 equals 1 times x minus 0. And if you'd like to simplify that a little bit, y minus 1 equals x, or y equals, excuse me, x plus 1. Okay, I'm going to sketch that just a little bit on this upper graph. Okay, I've got a y-intercept of plus 1, and, ooh, this is not very accurate. Yeah. Okay, let's pretend I didn't graph those extra points, and, okay, we draw the tangent line. Okay, so I now have an equation for this line, something that would be easy to plug in that doesn't involve any exponents or doesn't involve this irrational number e. So if I wanted to find y of 2, okay, I could get an approximate value by plugging 2 into the equation for my line. Okay, so y would equal 2 plus 1, so 3. Okay, so we're approximating that y of 2 is approximately 3. All right, so let's go ahead and I'm going to pull out my calculator real quick, check how close this is. Okay, so remember my, oops, let's get rid of linear algebra. Okay, my original equation was what I wanted to approximate this. So I'll put an e squared. Wow, very different. Okay, our approximation is pretty bad. Okay, but at least, you know, we're positive, we're within 4. Maybe NASA wouldn't accept this if we're going to the moon, but we're okay. You can see, though, if we get too far away from the point at which we did the tangent line, or we made the tangent line, our approximation gets really bad. Our approximation would have been really good, really close by. Okay, that was when we talked about linear approximations back in the day. But as we move further away, our line becomes less accurate. So we want to think about how could we change our approximation as our graph changes. Okay, and our answer is going to be, instead of using just one line, what if we use more than one line? What if we use this line to move a certain distance, and then we use another line to get closer? So for example, what if I use this line to get to 1, and then try to use a slope there again to get up to 2? That would be closer, right? And if I use even more and more and more approximate, using more and more tiny little lines, my approximation would get a lot better. Okay? So instead of using one big line, what if we use 2 lines in between? And that's what the next problem asks us to do. So I'm going to go ahead and flip the page. We call using, kind of breaking it down, we call that a step size. So here, me drawing 2 lines to go from 0 to 2 was a step size of 1. Okay? All right, well, this actually does not ask us to do 2 steps. This asks us to do more than 2 steps. Okay, because I'm still trying to go from 0 to 2, but I want to have a step size of 0.5. So this should be even more accurate approximation. That means I'm going to need at least, what, 4 steps? 0.5, 1, 1.5 to 2. So I'll need 4 steps. Here is where Euler's method is coming in. And this is actually how Euler, back in the day, would approximate values without having a calculator, by using linear approximations just over and over and over again. So we're kind of become a little machine. And there's a nice table I'd like to use to keep us organized when we're doing this method, especially if we're going to have to do it 4 different times. So first, we're going to have the point that we're currently at, xy. Okay? Then we're going to say, how much does x change? delta x. That's going to be our step size right here, the whole way down. The step size should never change because we're stepping the same amount every time we move across the x-axis. So I'm trying to figure out what this delta y could be, because this is going to be super easy to find, change in y. So let's go back to the last page really quick and take a look at what a linear equation looks like. So right here was our linear equation, our tangent line. I'd like to rewrite this a little bit differently. If I'm looking for this y value and I'm subtracting another y value from it, because that was the point over here, we can also call the left side delta y, a change in y. This is our slope, which you can call dy dx, or if you really like, you can call it m. And we're multiplying that by a difference between two x values. So that will be delta x. So if I'm looking for the change in y, I can find it by using the formula, the derivative times delta x. And I'm going to add that to our chart over here, just so we're reminded of how to calculate this. This will actually be the only column that we will actually have to do any kind of calculus or just math in general. So I'll write this as dy dx times delta x. Okay? And then just to keep us organized, our new x and our new y. Okay. Now, why do we have all these columns? What is this process? This is a way for us to kind of organize our thinking and to go from one step to the next. So I am trying, let me go back to my diagram over here, to approximate y of 2. I'm trying to get something close to this value. But what I have to do, in my very simple example, if I only take 2 steps, one, I have to go from the point I started at with my first tangent line to this new line. It's an approximation for y of 1. Then I would like to use the derivative at y of 1 to make a new line to kind of reflect the change in how our graph is sloped. But that means I have to recalculate the derivative and redo kind of the addition, because I'm going to be adding something on to this point rather than this point. Okay, so let's work on organizing our first step. So what point are we starting at? Okay, the initial point that we were given, our initial condition, is the point 0, 1. Okay, how much is x going to change? That's our step size, 0.5. And that's going to be the same all the way down. So we're not going to write anything else. If you want to skip ahead a little bit, you can go ahead and say, okay, x plus the change in x will be our new x. So that will be 0.5. Okay, and now just to remind us from the last page, our dy dx was equal to y. Okay, so if I want to find the change in y, I'm going to say dy dx at this point. So I'm using the slope at this point. Okay, so the slope at this point is 1 times the change in x times 0.5. So that's equal to 0.5. Okay, so that's my change in y. 1 plus 0.5 is 1.5. Okay, and that is where I'm going to start the next step. This was all the calculation I did to make that first little tiny tangent line. Now I'm going to make the second tiny tangent line and connect them together. So I'm starting now at my new point, 0.5, 1.5. My change in x is still the step size, 0.5. My change in y, though, now is different because I'm taking the derivative at a different point. So now my dy dx will be 1.5, again, because my equation for dy dx was just equal to y, times delta x, so times 0.5. Okay, so I'm looking for basically 1/2 of 1.5, which is 0.75. Okay, and you can see that this is definitely going to be one of those things where we're probably going to need a calculator to get into some of these nitty-gritty decimals. So my new x will be my old x plus my change. So now I'm at 1. And my new y will be 1.5 plus 0.75, which will be 2.25. Okay, so I start over. I'm halfway there though, because this is my new x, and I'm looking to get to 2. So I'm halfway there. So 1, 2.25. My step size is still 0.5. But now I need to multiply my slope, 2.25 times 0.5. Okay. Oops, forgot parentheses. All right, and I'm going to get a little lazy. I'm going to put that in my calculator. Okay, so I will get 1.125. Props to you if you did that in your head. Okay. My new x is x plus the change in x, so 1.5. My new y is y plus my change in y. So that will be 3.375. Okay, but notice we're almost there. We have one more step of 0.5 to get to 2. So last time, we're starting at 1.5, 3.375. My step size is still 0.5, and now I'm going to need to multiply 3.375 times 0.5. Put it down here. Ooh, and I get 1.6875. It is really, really, really important that you do not round until you get to the very end of your table, until you get to your final answer. If that means that you need to store some of your decimals, like store some of your change in y's, to do your calculations, do it. But do not round until you get to the very end. Okay, so my new x is x plus my change in x, which is 2. Hooray, we're here. And then y plus my change in y. So I will add 3.375. Which is, sorry, the dogs and I are at home alone today. 0.625. Okay. All right, and then remember. Woo! Oh my gosh! Remember, we were trying to approximate e squared. Excuse me, and that was 7.389. That's much closer than it was before. So the point is, if we use more steps, we get a more accurate approximation. Remember that back here we used one step. We literally went straight from 0 to 2 in one step, and that was way too far. We only got an answer of 3, which is much, much farther off than what we were looking for here. Okay, so conclusion. Our approximation when we took more steps was closer to the true value. So how can we improve our approximations? You could say smaller step size, which results in more steps. Okay? All right. And you can think about this also in the same way we thought about arc length. Remember when we did arc length, we measured the curve by measuring the length of teeny tiny tangent lines. Same thing here. The more steps we have, the smaller our little dx is, or smaller our change in x is, the more accurate our approximation will be. Okay, I am going to leave example 1 here for you to try yourself, but look for it to be filled in on the filled notes. Notice we have an initial condition of y of 0 is 1, and I would like you to use the step size of 0.2. So you're going to have to take at least 5 steps in this case. Be really, really organized. Remember, do not round in the middle. And notice that our slope here depends on both x and y. So you will need both the x that you're on and the y that you're on to calculate this slope. But let's go ahead and move on to slope fields. Okay. Oh, here's another practice problem. Okay. Slope fields. So what a slope field is, as many of you who took the practice AP exam found out, is it's literally just a field full of little lines, or you could kind of think about them as vectors, that describe the slope at each point in this plane. Okay, so here the notes will say, like, you'll be given a point and you'll come draw it on the board. But I'll just do a couple for us just to get us used to it. So let's say this is my slope equation that I would like to draw here. Let's say that I chose the point 0, 0. Okay, at the point 0, 0, dy dx is 0 minus 0. So the slope is 0. That looks like a little horizontal line, and that's hard to see, but hopefully you get the gist. All right, what about at 1, 0? At 1, 0, the slope is 0 minus 1, which is negative 1. So at 1, 0, I should draw a little line that indicates that my slope is negative 1. Your slope should try to be relatively accurate, but I know that this is not, you're not drawing it for very far because it only applies at that point. So make sure just if you get a different value, you try to make it steeper or less steep than the ones you I've drawn before. All right, so let's try, if I do 0, 1, my slope is 1 minus 0, make it 1. So at 0, 1, I should have a slope that looks like this. Okay? All right. Notice you can also think about you can think about it not point by point. You can also think about it as where would this slope be equal to 0? So where would the slope equal 0? So 0 equals dy dx. Well, that's just where y equals x. So anywhere along the line y equals x, I should have a slope of 0. So we get kind of a pattern going across the whole field. Okay? And then you can also think about when would it be negative, when would it be positive, but I like to kind of just think about slope 0 because that helps me eliminate some of my choices or kind of look for a pattern in the field. But you would just repeat this with as many points as you would like to kind of get an idea of what this might look like. If you have a slope field that is already filled in, like the one on the next page, what it's really illustrating to you is all of the possible general solutions that you could choose. Okay, so all you would have to do is pick an initial point and follow the slopes as they go around. If I'm given an initial point, I can illustrate a particular solution to this curve. Okay, so let's say I was given the point 0, negative 1. If I was given this point as my initial condition for this slope, then I would just kind of go through my initial condition and go around following the slopes. Now, it's not perfect. This is why the AP test doesn't grade you on your drawing. But notice that I did make a circle, just like it indicates in the overall graph. And we'll do this again later down here with another point. But first, let's just go through a couple of the questions to see what kind of information we could get from a slope field. So, for example, I can find the slope at these points and then kind of check my answers using the slope field. So if I wanted to find the slope at the point 5, 2, I would get negative 0.36 times 5 over 2, which I will go ahead and put in my calculator. Okay, so negative 0.9, almost negative 1. So let's go over to 1, 2, 3, 4, 5, comma, 1, 2. That sounds about right. Okay, so that's the point we just did there. You can also go ahead and check negative 8, comma 9. Let's go ahead and look at it. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so I've got something a little bit positive, but kind of a small decimal, but definitely not as much as 1. So we'll look for something positive, but closer to 0 than closer to 1. Okay, so if I are given an initial condition, just like I described earlier, I could draw a graph representing the particular solution through that point. Okay, so let's go ahead, I'll draw it in a different color, and go to 0, 6. So this was 5, 6. Oh, excuse me, 0, 6. 1, 2, 3, 4, 5, 6. Okay. All right, so, and we'll try to be as accurate as we can, but this just takes kind of practice. And you're right, it's difficult to know kind of where should we go? How should we follow? And this is why this is not something you would really be graded on the AP test. Ooh, that's not symmetrical. So let's try that a little bit better. Ugh. All right, you can see how difficult this kind of is. So we'll just give it our best estimate. I'll keep it over there. Okay, given the shape of this, I'm relatively certain that this is going to be some kind of ellipse. So I'll also go through the point 0, negative 6. 1, 2, 3, 4, 5, 6. Also a very inaccurate graph. You can see that this is Miss Kelly's weakness. So hopefully your drawing is a little bit better. But again, the gesture is just to kind of follow the slopes around the field. Again, this kind of seems to be an ellipse. Okay, if I start at 5, 2 though, where we started earlier, okay, this point right here, you can see that I'm getting a smaller ellipse. Okay, all right, there we go. Okay, how is the solution related to the previous one? It's smaller. Okay, and then solve the differential equation analytically. Something we can still do to check to make sure that the shapes of our equations are the right ones. So let me copy this down. So I have that dy dx equals negative 0.36x divided by y. Okay, separate. So y dy equals negative 0.36x dx. Integrate, and I get y squared over 2 equals negative 0.36x squared over 2 plus c, because they didn't really give us an initial condition. I guess we could have chosen one of them from before. But if you'll notice, okay, let's do the opposite of what we're supposed to do right now. Let's go ahead and put all the variables on the same side. Y squared over 2 plus 0.36x squared over 2 equals c. This, hopefully you recognize that maybe from Algebra 2, is the equation of an ellipse. Two squared terms being added together. So we can check and we can say, you're right. Even if we didn't solve for y, we can see that this is the right kind of shape for us to have drawn. Remember, if you did solve for y, you would need to write a plus or minus to get both the top half and the bottom half of the ellipse. Okay, and here are the examples that I'm going to leave for you to do and fill in on Google Classroom. But I want to help you out in a little bit. In order to determine which equation goes with which slope field, I want you to again think about where would, in this equation, what would have to happen in order for the slope to be 0. And once you figure that out, look for that pattern on this graph. You can also think about it in terms of quadrants. If both equations are positive, what kind of answer should you get? If both equations are, when I'm saying equations, I mean variables. If both variables are positive, what would you get? If both variables are negative, what would you get? Okay, what about if x is positive but y is negative? And what about the opposite? Those kind of patterns will help you distinguish what goes with what. And again, you have some of those prompting questions here. Okay, so look for things that are really easy to check. Here, notice that each equation this one is dependent upon y. This one is dependent upon x. So which one of them will be different when you change the y variables? Which one will be different when you change the x variables? Look for patterns and just shifting your variable to be negative or positive. What would happen? This takes a little bit of just kind of investigative math. Okay, so there is one more page over here, same thing. And then finally, an AP question from 2002. Okay, so here I want to point out a couple of things. They want you to sketch the solution curve that passes through these points. This is not an expectation for what they would ask you on a current AP exam, but good practice for going ahead and trying to figure out what kind of solutions would happen. Notice that this point right here is kind of in the middle of this linear function. That's okay. Your solution curves don't all have to look the same. In fact, these two should look very different because we're having two different patterns of slopes based on where they're located. This one's going to be kind of linear. This one is going to be kind of curved, maybe even approaching an asymptote here. Part B, we're asking for Euler's method, starting with a step size of 0.1 to approximate 0.2. Well, that's two steps because we start at x equals 0, step size of 0.1, we're going to 0.2. So very easy, 2 steps. This is a non-calculator problem though, so you should expect to try to do this on your own. Okay. Here, we've got find the value of b for which this is a solution to the differential equation. So where would we graph a solution? Okay, where would we graph a particular solution that would be linear? You've already kind of answered that question in part A. So think back to what you graphed in part A. Okay, and then part D, we're looking for local extremum. Okay, so think about what local extremum means. That means max and mins. What would you need to have to find your max and mins? Well, you already have it in this problem. So you don't have to integrate here. Okay, be careful. You have all the information you need in this. All right, make sure you look at the field notes to check your other work and to kind of finalize any misunderstandings. I'll make sure to write annotations on this field work.